In this lecture, we'll start off by looking at Dmaic, which stands for Define, Measure, Analyze, Improve, and Control. Most companies use the Dmaic structure to guide their Six Sigma activities. After that, we'll examine basic statistics. Many of the Six Sigma methods and tools that you'll learn about later in the course require you to have a basic knowledge of statistics. So I want to make sure that you're well prepared. I'm not exactly sure who coined the Dmaic acronym, and let's admit it, it's not the easiest to remember, but it's been around for a while. When I first encountered it, it seemed to be an update of Walter Shewhart's well-known Plan, Do, Check, Act Pdca cycle from 1939, later called the Deming cycle. The four phases of Pdca are recognize an opportunity and plan the change, test the change, review the test, analyze the results and identify lessons learned, and take action. Dmaic improves upon Pdca because it more specifically cites two vital actions, improve and control. While it's not critical that you use Dmaic, it's beneficial for a few reasons. First, it's important to standardize terminology. This improves communication and prompts people to agree on how to proceed. Miscommunication is a barrier for process improvement and many more topics. If one person says he uses Pdca and another says she uses Dmaic, well, you get the picture. It's noteworthy that the American Society for Quality, ASQ, uses the Dmaic structure in their Six Sigma body of knowledge for the black belt exam. If ASQ uses Dmaic, that should be good enough for anyone. Let's look at each of the stages. First is define. If you review the teachings of the quality experts, all of them state that improvement must begin with process definition. If you don't understand how something works, how can you make it better unless you're lucky? In his book, The New Economics, Dr. Deming coined the term tampering to describe what happens when people try to improve a process before they define it. Tampering usually makes things worse. So what do you define? Everything related to a process, including who works on it, who benefits from it, how it works, what it produces, and what you want it to produce. Next is measure. This stage uses metrics, also known as measurements, to communicate how things are going. It's essential that you set a baseline using valid and reliable data. This baseline will indicate where you begin and will help you chart progress. One key measurement is sigma. When you achieve Six Sigma, you will produce 3.4 defects per million opportunities. Next, we have analyze. When you analyze a process, you identify problems. You can develop theories about their root causes, verify your theories using data, and arrive at a solution. This enables you to reduce the gap between what you have and what you want. You'll spend the largest percentage of your time in the analyze stage. Then comes improve. In earlier times, it would have been tempting to call it Dmaic and leave out the I for improve. But as you know, just getting by won't help you succeed. Improvement is the name of the game. It's not enough for a process to satisfy today's customers. In the improve stage, you'll implement your solution from the analyze stage. And you also need to keep an eye to the future. You need to improve processes so they meet future requirements. You need to find new ways to do things faster, better, cheaper, and safer. And then we have control. Control is one of those words that have a negative connotation. Many people view control as something harsh or restrictive. The best way to view control from a Six Sigma point of view is getting what you expect. When you implement a solution, you want it to stay fixed. Control helps you do this. The best way to exercise control is by using a team approach and relying on data. If everything turns out as you plan, you don't need much control. The key is to obtain updates to keep you up to speed regarding how a process is performing. Now that you understand the basic DMAIC structure, let's move on to our study of basic statistics. There's a lot of information related to this slide, so pull up a chair and get comfortable. I imagine that many of you have had a statistics course or two in the past, but you know the old saying, if you don't use it, you lose it. I hope that our brief discussion of statistics today will help refresh your memories. There are two types of statistics that we need to gain an understanding of. The first type measures location of data, and the second type measures how much data differs. Many people love to work with numbers. I remember a classmate in one of my elementary school classrooms who could add a series of numbers in his head faster than anyone else could do using paper and pencil. I guess you could call him a human calculator. For the vast majority of us, we need numbers that are arranged. In statistics, this is called ordered and classified data. It's difficult to understand much and make inferences when you only have unordered or unclassified data. For example, if I'm compiling times at a bicycle race for 500 contestants, and I arrange their finish times by their entry numbers, it's difficult to determine how this year's racers compare to previous years. One way to organize data is by using visual images. Later on, we'll take a look at a few methods to help you visualize data. When you use statistics, you improve upon visual images because it is more precise. Statistics describes physical conditions and situations by using two indicators, measures of location and measures of dispersion. Statistics are very helpful in describing large populations. For example, assume that you are interested in the heights of basketball players of all ages in the entire world. How would you have a meaningful discussion with someone about this topic? You may be able to identify the shortest and tallest players, but what else could you say? Measures of location, also known as measures of central tendency, provide data about this topic. The measures of location are the three M's, median, mode, and mean. Let's review each of these M's. While this information may be review for many of you, it's important that I discuss median, mode, and mean before we get too far along. Median, first, you find the median as a value position in the middle of a group of data. Personal income can be stated in terms of the median. Before you can find the median, you need to sequence your data in ascending order. When you have an odd number of data points, you find the median by locating the middle position. Suppose that my nephew is doing research on personal income. He finds that the median income in Oregon and Washington is $55,000 and concludes that people in these two states make about the same amount of money. Hold on, how can this be when the difference between the highest and lowest income in Washington is $110,000, while in Oregon it's only $55,000? I think I better send my nephew back to do some more homework. The point is that the median is limited as a statistics. Unfortunately, too many people call it an average, which may be misleading. Too often it doesn't give an average. Next, we have the mode. The mode is defined as observations that occur most frequently. Some populations do not have a mode because there is no value that occurs more than once. And you may have a multimodal population where there are two values that occur at the same frequency. Then we have mean. Many people also call means averages. However, in statistics, the word average is not a recognized term. So far, the 3Ms haven't helped us understand much about what we are studying. Fortunately, the measures of dispersion will give us some help. To ease our way into the measures of dispersion, we need to start with the normal curve. The normal curve in statistics, the mean is represented by the symbol x bar. When you understand the concept of the mean, it helps you understand the normal curve, also known as the normal distribution. The normal curve is a continuous distribution. Variables in a continuous distribution can take on any value in a possible range. Examples are individuals' weights, distances that various automobiles can travel on a gallon of gas, and the times that it takes for light bulbs to burn out. Much of the variation in nature and industry follows the frequency distribution of normal curves. Runner speeds and dimensions of steel bushings are examples. A few hundred years ago, scientists found that many measurements produced data in distributions with relatively the same shape, which in statistical language is called symmetrical and unimodal, balanced and no data point occurring more than another. You may also know this distribution as the bell-shaped curve. Although the shape of the normal curve resembles a bell, it can be a tall, thin bell or a short, broad bell. Also, the bell can move around because of the location of the mean. One of the greatest assets of a normal curve is its ability to predict. When you consider the heights of human beings, you expect a small percentage of them to be extremely short and a small percentage of them to be extremely tall. The normal curve has most of the values clustered near a central point, average heights, with progressively fewer values positioned away from the center. It is symmetrical about the central point because it spreads out evenly on both sides. The values away from the center represent short and tall people. Statisticians use the terms shape, center, and spread to describe the normal curve. When we calculate a curve's measure of dispersion, it provides additional insights. Measures of dispersion, also known as measures of variation, help us learn about the differences for members in a population. The first measure of dispersion to talk about is the range. The range is the simplest measure of dispersion. To find the range, sequence data in ascending order and subtract the smallest value from the largest. Mean absolute deviation is another term that is used. Let's simplify because the phrase mean absolute deviation is almost too much to take. The good news is that if we look at each word one at a time, we can understand it. Then we have variance. I think you'll be happy to hear that when you learn how to calculate variance, you almost learn how to find standard deviation at the same time. You just need to take one extra step. Most people prefer using variance instead of mean absolute deviation because it's not necessary to work with absolute value. Although variance is easy to find, it does have a disadvantage. Numbers become quite large in no time flat. Standard deviation is a snap once you find variance because it's basically the square root of variance. Now, I've found that far too many people don't know how to use or explain standard deviation, even those who have just completed a statistics course. It's my goal to make sure that you understand standard deviation. So, according to the normal distribution, 34.13% of a normal population occurs within plus 1 standard deviation, and another 34.13% occurs within minus one standard deviation. This means that 68.2% of quiz scores may occur within plus or minus 1 standard deviation of the normal curve. And as you move forward out to the extremes, we find that 95.46% of occurrences happen within plus or minus 2 standard deviation. Then finally, 99.66% of all occurrences happen between plus and minus 3 standard deviation. I hope that you found this introduction helpful. The most important thing to remember is how to use SD. Remember that it's used to describe distance from the mean and therefore helps you understand the characteristics of the normal curve. The greater the SD, the greater the spread, and the smaller the SD, the less variation in a process. That concludes our lecture for today.